Hello and welcome to the Chemistry Academy. In this video we're going to go over equilibrium calculations in relation to the Advanced Higher Chemistry course. So let's get into it. Okay, so let's start off with our first example. So in this example we've got ethanol reacting with ethanoic acid as follows in the given reaction here. And then it tells us that 1 mole of ethanoic acid and 2 moles of ethanol were mixed in a sealed 1 litre container. At equilibrium, 0.92 moles of ethyl ethanoate were present. Calculate the value of the equilibrium constant K. So this is how I like to lay out these questions, and these are the words I like to use within my layout, but there are different ways you could do it and different words you could use. So just find whatever words resonate with you and remind you of what stage of the reaction the concentrations are at, and what the numbers actually are referring to in the context of the reaction. So hopefully that'll make more sense when I start to go through it. So I would always rewrite the equation again, just because there's not really very much space to write stuff underneath the equations in the question normally. So don't worry about the state symbols because they're not really necessary when it comes to the calculation, although you will need to bear in mind for this question that because water is a pure liquid, it is actually omitted from the calculation because it's assigned the value of 1 when it comes to equilibrium constants and expressions, so it's not going to make any difference to the equilibrium constant. So it's just the other ones that we really need to worry about. So copy the equation down, and then I'll just remind myself that I don't need to worry about the water. So the words I like to use are start, because that's what we have at the start of the reaction, when the reaction's first beginning. Then I like to use in the middle the terms used stroked made, because it reminds me of how much of the reactant's been used, how much of the product has been made. But again, like I said, if you've got other words that you would rather use, then you're more than welcome to change them up. And then for the last word, I like to use the word end. You can use the word equilibrium, it doesn't really matter, whichever suits you. I'll maybe go with equilibrium though, just because we are obviously calculating equilibrium constants, so it might be less confusing for people. When it comes to this middle line, the used made line, in this line all we're doing is applying mole ratios. Okay, so I like to also then add in a little reminder just to use the mole ratio. Okay, so if we go back through the question, it tells us we've got 1.5 moles of ethanoic acid at the start, as well as 2 moles of ethanol. So if I write those under the chemicals, 1.5 moles of ethanoic acid, 2 moles of ethanol, and then it says that at equilibrium 0.92 moles of ethyl ethanoate were present. So that's a concentration at equilibrium, or quantity at equilibrium, of the ester. So I'll write that next to on the equilibrium line, next or underneath the ester. If then there was 0.92 moles of the ester at equilibrium, then that means that that's how much was made. Okay, so 0.92 moles were made at equilibrium. Now that we've got a number in that middle row, we can use the mole ratio in the reaction in order to work out how many moles of the reactants were used. So because it's a 1:1:1 ratio, that means that it will be 0.92 moles of each of the reactants being used. Okay, because it's 1 mole to 1 mole to 1 mole, so if you made 0.92 moles of your ester, you must have used 0.92 moles of your ethanol and 0.92 moles of your ethanoic acid. To then work out how much of the reactants we had at equilibrium, that's essentially working out how much we've got left, so we just need to subtract. So if we do 1.5 take away 0.92, we get 0.58. So that's how much of that reactant was left at equilibrium. And then for the ethanol, we would do the 2 moles minus 0.92. Could probably do this in my head, but I'm not going to take any risks. And then that would be 1.08 moles for that one. Okay, now we know what all the concentrations of things are at equilibrium. We can then write our equilibrium expression in order to calculate the equilibrium constant. So remember, it's always products over reactants, so it'd be CH3COO C2H5, and the water is omitted because it would be assigned the value of 1 anyway. And then CH3COOH times the concentration of C2H5OH. Okay, so then I just plug the numbers in. So the concentration of the ester at equilibrium was 0.92, and then that's over 0.58 times 1.08. So if we put this in our calculator, we will get 0.92 divided by, big flips, bracket 0.58 times 1.08, which gives us 1.469 if we round it to 3 decimal places. And just remember, equilibrium constants don't have any units, so it's just your number. So if we do move on to another example, so this one is slightly different. In this one we've got dinitrogen tetraoxide dissociating to form nitrogen dioxide according to the equation they've shown. And then it says 0.56 moles of N2O4 gas is placed in an empty 1 litre flask and heated to 150 degrees. When the system reaches equilibrium, 0.32 moles of N2O4 remained present in the flask. Calculate the equilibrium constant K for the reaction at 150 degrees. So the reason they're telling you the temperature is to confirm that the temperature you're trying to calculate the constant at is the temperature that the reaction was at. So you don't need to use the temperature in your calculation, it's just kind of there as confirmation for you that the temperature hasn't changed. If the temperature just does change, it's actually impossible pretty much to calculate what the equilibrium constant would be. You would need to know the concentrations at equilibrium at the temperature that you want the equilibrium constant calculated at. So that's just an aside, so don't let the temperature being there confuse you. You don't actually need it in these types of calculations. So again, if I write out the equation, so N2O4 and then 2NO2. So I'll have my start, used, stroke made, and then end lines. And just remember, the middle line is the one we're interested in, and this is where we apply the mole ratios. Okay, so I'm just going to leave a wee note there for myself to say mole ratio. So if we read through the numbers again, so it was 0.56 moles of N2O4 gas placed in the empty cylinder, so that's how much of that we had at the start. And then when the system reached equilibrium, there was 0.32 moles of N2O4 remained, so that's how much was then at the end, 0.32 moles of N2O4. So you can see this one is a bit different because we don't have how much product we made or how much product there is at equilibrium. We only know how much of the reactant is left, but we have enough information to work out how much was used, so how much of our reactant was actually used up. So again, we just do a subtraction. So if we do the 0.56, take away the 0.32, we would get 0.24 moles. Okay, that means then we can apply, we've got a number in this middle row, so we can apply the mole ratios and work out then how many moles of everything else there is. So this time it's a 1:2 ratio, so that means that we just need to times this 0.24 moles by 2 to get to the number of moles of NO2 that must have been formed at equilibrium. Okay, now that we know how much of that has been made, then that's how much we would have at the end. Now we have all of the numbers that we need at the end of the reaction. All we have to do is write up our equilibrium expression and plug the numbers in. So again, K equals, this time it's the concentration of NO2, and that has to be squared because there's 2 moles of it in the reaction. And then on the bottom we have the concentration of N2O4. Okay, so then if we plug in our numbers, we have 0.48 squared over 0.32. And if we put that into our calculator, so 0.48 squared divided by 0.32, we get 0.72. And again, there's no units, so Sorry, that 2 looks a bit weird. Okay, and that's that one. One more example, just to finish off, because they do say third time's the charm. So I'm not going to read through the question this time. You can read it here for yourselves. I'm just going to start off, so I'll write the reaction again. Again, don't worry too much if you are copying it down about copying down the state symbols, because you don't really need them if they're already there. So then our start, used, stroke, made, and then end. And again, just remind yourself that that middle line, this is where you just use the mole ratio to work out. So if we read through the question, at equilibrium, 0.25 moles of PCl5 is placed in a sealed 1 litre flask. So that's at the start, PCl5, so 0.250 moles of that. And then it says at equilibrium, 0.098 moles of PCl3 have been formed. So that means at the end, we had 0.098 moles of PCl3. That means that then we made 0.098 moles of PCl3. And now we've got a number in that middle row. Oops, we can apply the mole ratios. So because it's 1 mole, 1 mole, and 1 mole, then it means that this middle row is all going to be 0.098 for all of them, because it's 1 mole in the ratio for each. That means that then we had 0.098 moles of chlorine at the end, because that's a product. Okay. If it helps you, you can also separate the reactants and products with a line, if that makes it easier for you to remember, like where you're subtracting and where you're not. So then, because you don't obviously have any product at the start. So then to work out how much of the PCl5 we have at the end, we just need to do a subtraction. My mental math is not going to manage to do that. So 0.25 minus 0.098. That gives us 0.152. Oh, move the pointer. Okay, so then now we've got all the numbers at the end, we can set up our equilibrium expression. So K equals PCl3 times the concentration of Cl2 all over the concentration of PCl5. And there's only 1 mole of each one, so there's no powers that we need to place. They're all to the power of 1. So then if we plug in our numbers, 0.098 times 0.098 divided by 0.152. Okay, so if I put that in my calculator, so 0.098 times 0.098 divided by 0.152, and that gives us 0.063. And again, equilibrium constants have no units. So I hope that helped, you found that useful. If you did, please give this video a like, don't forget to subscribe and tell all your chemistry friends, and I'll see you again soon.